So benzene, one of the most storied organic compounds, and I'm sure your teachers at different levels have told you different versions of the story, so I'm not really going to mess with it. But benzene anyway is C6H6. Now, first thing to do is look at that formula and compare it to hexane in terms of getting the so-called unsaturation. So hexane, C6H14, so we expect 14 hydrogens if all we've got single bonds. So we don't, we've only got 6, so we've lost 8 hydrogens, or 4 sets of 2. And if you remember previous discussions, when you have a double bond, you lose 2 hydrogens. When you have 2 double bonds, you'd lose 4 hydrogens. When you have a ring, you lose 2 hydrogens. So we have what's called 4 levels of unsaturation because we've lost 4 sets of 2 hydrogens. So we've either got 4 carbon-carbon extra bonds or rings. Okay. Now, for a long time, the structure of benzene eluded scientists in the 19th century until a chap called Kekulé, who would have absolutely nothing remembered about him at all other than the fact that supposedly he had a dream about a snake eating itself in a nice little loop, and so associate that with carbon-carbon ring, and the structure of benzene is this, as you see. Okay, there's the ring, so that's 1 level of unsaturation, and then 3 double bonds taking us up to the total of 4 levels of unsaturation, 4 sets of 2 hydrogens. So pretty, what a nice little pretty structure. Trouble is, of course, that it doesn't react like you would expect if it was just an alkene. We got 3 carbon-carbon double bonds, should react like 3 alkenes, but it doesn't. So why doesn't benzene behave like it just has 3 carbon-carbon double bonds? Well, let's have a look at the bonding in terms of orbitals to get an explanation for that. We're thinking of it as being localized double bonds. So in other words, there is a double bond here, single bond there, double there, single, double, single. Okay, now let's flip that nice flat 6-membered ring on its side and we get this picture. Okay, so coming out at us here, going away from us there, and let's remember that around each of these carbon atoms you've got the various sigma bonds that form single bonds, and then of course the bonds to the hydrogens that I'm no longer showing. But then perpendicular to the ring, each carbon atom has its own p orbital sticking up. So we've got 2 red colored p orbitals sticking up from those 2 atoms, and that's going to be one of our double bonds. We got 2 blue colored p orbitals sticking up from these 2 carbon atoms, and that corresponds to our second double bond. And then this is supposed to be yellow, except you can't see yellow, so it's a sort of fake weird yellow, and I know it doesn't look yellow at all, but pretend it's yellow anyway. So here's these 2 ones here that correspond to this double bond that's coming out at you, the double bond on the bottom there, like that. Okay, and now of course when we have p orbitals on 2 atoms that are going to overlap to make that pi bond, that double bond, it kind of looks like this. And again, massive apologies, taking artistic license here, but essentially here's the red pi bond sticking above and below, so that's because of this and this combining. There's the blue pi bond above and below the ring, that's these 2 combining here, and then you can see this one in the front a little bit better. There's the top part, the shady bits overlapping with each other, and the unshady bits overlapping with each other. So this would be a rather poor, but at least you can, I hope, see it, depiction of the pi bonding when we look at this structure. But wait a minute, what's so special about these 2 carbons that they double bond to each other? All we know is that we've got a ring and we have 3 double bonds in it. There's absolutely nothing wrong with instead drawing it like this. Now look at the differences here. Now instead of double bonds in this top structure, they're single bonds, and what were single bonds like this one at the top here in the top structure are double bonds in this second structure. So let's do the same thing, flip it over. Okay, and so there's coming out at us, double bond there, single bond there, there used to be a double bond there where used to be a single bond. Same orbital picture, except now I'm not going to be overlapping the orbitals of the same color, I'm going to be overlapping orbitals of different color. So my first one here is going to be kind of an orange between the red and the yellow. You see what I did there? And then this one here would be the overlap of red and the blue, and the overlap of red and blue is of course purple. And then down here we've got blue and fake yellow, blue and fake yellow make a not fake green. Okay, so this is what that overlap would look like. Again, we can see more clearly the one that's going horizontal, so there's the top and the bottom part of the overlap between the blue and the red there. There's the green because of these two overlapping. There's the orange because of those two overlapping. Okay, now I hope you can see that when you think that benzene could either have this structure or this structure, nothing wrong with that, and then when we look at these p orbitals that are overlapping like that or like that, well, there's really no reason why the p orbitals can't just all overlap with each other, thus making this sort of donut appearance. Okay, so there's the top part of the p orbitals overlapping, the bottom part of the p orbitals overlapping. So in other words, what we're saying here is we're not going to have localized double bonds, we're going to have delocalized bonds. Okay, and so when one draws a benzene molecule, a lot of the time you'll see that reflected in how we're doing it. We're not saying that this is a double bond or that this is a single bond. We're saying that, well, some of the time it's a double bond, some of the time it's a single bond, and so what we're seeing here is this attempt to draw that continual little donut here. Okay, you've got for sure at least one bond between every carbon, but then every position is halfway between a double and a single bond. Okay, so we have this delocalized pi bonding in benzene, and that explains all of the funny little things that we saw. It's not localized double bonds, it's delocalized multiple bonds.